2.5, polynomial functions and models. We're going to start with zeros and the relationships to the graph. A polynomial function has real and or non-real zeros, meaning imaginary. Real zeros correspond to the x-intercepts of the graph. And we've seen this before, or you've seen this before. When a graph crosses the x-axis, that's the x-intercept, that's a real zero. But the imaginary complicates it a little bit. Multiplicity of a zero. So this is kind of neat. If you see a multiplicity of 1, you can kind of think about x to the first, and an x to the first graph is just going to be like a straight line, basically. And so a zero with a multiplicity of 1 is going to cross at that zero, cross. But an even number, like 2, for instance, if you think about what x squared looks like, a zero with even multiplicity is going to bounce like an x squared graph does. A zero with an odd multiplicity that's not 1, like, for instance, x to the third, is going to kind of mimic an x to the third graph, and it's going to wiggle. It's kind of interesting how it shakes out. So with that in mind, we can do example 1, determine the multiplicities of the zeros. So you're looking for your x-intercepts. There's one here, and one here, and one here. Whatever they are, it doesn't matter what the numbers are. We're looking at what happens at those 3 points. And so since the first one just crosses, it looks kind of like a line. That's going to have a multiplicity of 1. I'm going to call that M1. The second one looks a lot like a parabola. I'm going to call that M2, even though really it's an even number. We know it's an even number. It's not necessarily 2. It might be 4 or 6 or something, but usually it's just going to be 2. And then the next one, it doesn't really wiggle. It more goes straight through. So that's going to be a multiplicity of 1. Over here, we see an x-intercept. We see a 0 with a multiplicity of 1. And then this one right here, notice that wiggle. We're going to call that M3. Even though it's really odd, but not 1. It's usually going to be a 3. So it's kind of cool what happens. We can see the zeros, we can see where it crosses, but we can see a little bit of behavior with those multiplicities. End behavior of a polynomial is determined by its dominating or first term. First term. So if you look down at example 2, the first term is just whatever this thing is right here. You look at that and you can tell what the graph does at the end. And there's only 4 possibilities for a polynomial. If that first coefficient is positive with an odd power, we're looking right here, positive number, odd power, negative number, odd power, positive number, even power, negative number, even power. It's only those 4 possibilities for what the end behavior of the graph looks like. Now, we may not know what happens in the middle of the graph. I'm just talking about the end behavior. So either it's down and up, or it's up and down, or it's up and up, or it's down and down. Those are the 4 different possibilities. A polynomial of degree n has at most n minus 1 turning points with at least 1 turning point between successive zeros. So I know that's kind of tough for people, but when it's a degree n, we're looking at most n minus 1 turning points. It's not that bad once you understand it. Determine the end behavior in the maximum number of turning points. So that's what we just talked about right here. Here, let's all right. This is a positive even. And so if you look in your chart at your positive even looks like this one. So your end behavior is going to be up and up. That's your end behavior. This is a negative odd Negative odd looks like this one. So your end behavior is going to be up and down. Positive odd. Positive odd is this one. Positive odd. End behavior down and up. Negative even. Negative even is this one. Down and down. Again, I don't know what happens in the middle because I don't know what the rest of the numbers are, but I'm just talking about the end behavior, and that first term is enough to determine that. Now, as far as the turning points, I know that language looks kind of confusing, but we look at the degree and then we subtract one. That's what we're doing. So this has a degree of 6, so it's got maximum of 5 turning points. This is maximum. It's not necessarily going to have exactly 5, it's just going to have up to. This is a degree 3, so it's going to have a maximum of 2 turning points. All I'm doing is subtracting 1. Degree 9 has a maximum of 8 turning points. Degree 4 has a maximum of 3 turning points. And if you think about what that means, if we have, let's say we draw a graph here, and here's our axis, and our graph goes down and then up and then down. All right. Think about where I switched from down. This is going down, and then it turns, and now it's going up, and now it turns, and it's going down. I see 1, 2 turning points. That's what I'm talking about. So something with 5 turning points. Okay, there's 1, 2, here's 3, 4, 5. Now I've got 3, 4, 5 turning points where the graph turns and goes from increasing to decreasing or otherwise. How to graph a polynomial. Step 1, find and graph the real zeros. Real zeros. Use the rational zeros theorem if needed. This is what we did in lesson 2.4. Section 2.4, we did a lot with finding zeros. We did a lot of synthetic division to find zeros, so we're going to have to go back and do some of that. Number 2 says determine the end behavior. Okay, that's what we just did. 3, use multiplicities to determine if the graph crosses, bounces, or wiggles. 4, make an XY table and plug in 0. 5, plug more numbers into your table, basically. So that graph doesn't really do anything. It's just an example of a polynomial. That's something like what we might graph. All right, so of course you could just type that on Desmos, but we're trying to learn how to do this by hand. If you go back to the steps, step 1 said find the zeros. So step 1, let's find zeros. And so we have to go back to section 2.4, and that's where we said, let's look at the factors of this number and the factors of this number, and we divide those and try to just figure out something that's going to work. We know there are at most 3 zeros, 3 real zeros, but let's just try stuff. And so let's try positive 1, see if it works. 2, 3, negative 11, negative 6. Add down and multiply, add down and multiply, add down and multiply, add down. That does not work. So let's try negative 1. 2, 3, negative 11, negative 6. Add down and multiply. Whoops. Add down and multiply. Add down and multiply. Add down. This does not work either. Negative 1 does not work. Let's try 2. Add down and multiply. Add down and multiply. Add down and multiply. Add down. Okay, great. This one works. That means one of my zeros is 2. Right there. One of my zeros, one of my x-intercepts is 2. But it also means that I've just broken down my problem from an x cubed into an x squared. So we can factor or use quadratic formula, I suppose, to try to figure out the other zeros. I like factoring better. I think it's a little bit faster once you know what you're doing. 2 numbers to multiply to 3. Those numbers do not add up to 7, and that's because the number over here on this side is getting multiplied by 2. So you want to think about how can I multiply by 2, and then they'll add up to 7. And you're like, well, if I multiply that one, it's going to work. So the 3 gets multiplied by the 2. That means I'm going to put a plus 3 right there and a plus 1 right there, and that's factored. I can find my zeros. I've got negative 1/2 to negative 3. It's kind of hard because your graph's so small, but you've got negative 3 here and negative 1/2 here. Step 1 said find the zeros. Step 2 said determine the end behavior. So step 2, end behavior. Well, that's when we look at this, okay? I see a positive, odd first term, okay? Positive coefficient with odd degree, and so I know positive odd is going to go uphill. Positive means it's increasing, and odd functions do that. So, I don't know if it's smart to go ahead and draw this on there, but that's what it's going to do. I probably would hold off on that just because it's hard to make the numbers fit, but that is what's going to happen. We know this. Step 3 said use multiplicities. Well, our multiplicities our 0 of 2 only happens once, and this one only happens once, and this one only happens once. Remember, a multiplicity is like a repeated value, okay? And so I know that it's just going to cross. It's going to cross, cross, cross. There's no bounce. There's no wiggle. It's going to just cross the x-axis at each of those 3 points. Number 4 says make an xy table. And it says plug in 0, but really you can plug in anything you want. If I plug in 0, that's going to be really easy because everything's going to fall out. Fall out, fall out, fall out, that's 0. I get 0, negative 6. Okay? 0, negative 6. 1, 2, 3, 4, 5, 6, right there. Now, if I know end behavior is down and up, and I can kind of just make this fit. It's going to look something like that. But I want to be a little bit more accurate. So I might do some more points. And that's what step 5 is. Step 5 is do some more points. But check it out. I already plugged in 1 and got negative 12. So when x is 1, y is negative 12. Use your table from before. When x is 1, y is negative 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is down here. 1, negative 12. But I also plugged in negative 1 and got positive 6. Negative 1, 1, 2, 3, 4, 5, 6. I don't really need a whole lot more points. Maybe I'll plug in negative 2 and see what happens at negative 2. Negative 2. So you can always just plug stuff in. 2 times negative 2 cubed plus 3 times negative 2 squared minus 11 times negative 2 minus 6. That's going to be 8 times 2 is 16. That's going to be 3 times 2 is, or 3 times 4 is 12 plus 22 minus 6. That is going to be, oh, that was a negative. That's going to be negative 16 right there. Negative 4, positive 18, positive 12. That's positive 12. Use a calculator. That's positive 12. So at negative 2, we're going up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 right there. Right. I'd say that's probably good enough to draw a decent looking curve. We've got down on this side. All the way up through here. Oh, I missed. Let's try that again. Kind of hard to hit it. Looks something like that. Something like that. That's not perfect, but pretty good. Number 4 is a little bit easier because the first step is easier. Step 1 was find the zeros. Well, we can see right here, negative 2 is a 0 and positive 1 is a 0. Okay, so we've got negative 2, and you might as well do the multiplicities while it's obvious. Negative 2 has a multiplicity of 3. That's the exponent right here. And that means that it's going to wiggle. This graph is going to wiggle at that negative 2. Negative 2 is right here on the graph. It's going to wiggle there. The 0 of 1 has a multiplicity of 2. Again, that's just the exponent. It's a repeat. We know it's going to bounce. There's a 0 at 1, and it's going to bounce there. So step 2, talk about the end behavior. The end behavior is not obvious for a lot of people here. And that's because you really need it all multiplied out. So if you've got x plus 2 cubed times x minus 1 squared, I don't need to multiply all of this out. I'm not going to. See how you're going to have an x cubed in there? You're going to have more stuff, but you're going to have an x cubed in the front. And here you're going to have an x squared in the front of this one. Whatever that expands out to, I don't have to do all of it. Once I multiply everything out, it's going to end up with x to the 5th, because that's multiply, plus blah, 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 whatever. I don't care. It doesn't matter. It doesn't matter. So you've got a 1 x to the 5th as your first term once you multiply all that out, and you should be able to see that. I'm going to have an x to the 3rd times an x squared. That's going to be an x to the 5th. And so I've got a positive odd. Positive odd has end behavior down and up like that. It's increasing. They're opposites. So you can kind of see it's going to be down. There's going to be a wiggle. It's going to come here and bounce, and it's going to end up. It's going to look something like that. Now we want to be more accurate than that, so I'm not altogether happy. Step 3. Multiplicities already did that. Step 4, make an XY table. So this was step 3. Step 4 is going to be a table. And we can plug in whatever we want really, but step 4 says plug in 0, just mainly because it's going to be easy to do. That's going to be 2 cubed, which is 8. That's going to be negative 1 squared, which is 1. 8 times 1 is 8. You've got 0, 8. Right there, 0, 8. And I don't know, we can plug in other stuff, but let's plug in negative 1. That's 1 cubed is 1. That's negative 2 squared is 4. Plug in negative 1, you get 4. Negative 1, 1, 2, 3, 4. Okay, pretty good. Tell you what you don't want to plug in is like negative 2. You don't need to because you already know negative 2 will give you 0. We already know this. Negative 2 is a 0, so is positive 1. So we've already got those graphed anyway. We just need to draw a decent curve. So again, don't forget your multiplicity says that this is going to wiggle. It's going to go up, come down. It's going to bounce and end up high. Something like that. That's not perfect, but it's pretty good. Intermediate value theorem looks really confusing, but it makes sense if you really think about it. You might have to read through this more than once. Suppose some function is continuous on this interval from a to b. So all I mean is we can trace it. Here's a, here's b. I can trace it without picking up my pencil. I can trace this function from a to b. Think about the domain, not the range. And it's continuous, so I don't have to pick up my pencil. It says there's some number c that's in between what you get when you plug in a and b. There's some number c that you get when you plug in a and plug in b. That c is between those two values. Then there must be some value of x between a and b such that when you plug in x, you're going to get c. Now that's kind of a weird thing. It's not that useful until you look at the extension of IVT, the extension of the intermediate value theorem. If f of a and f of b are opposite signs, there's at least one real zero between a and b. What that's trying to tell you, well, let's just look at example 5. Use the intermediate value theorem to show f of x must have a 0 in the interval from 1 to 2. What we're going to do is we're going to plug in 1. Plug in 1. If I plug in 1, you have negative 1 cubed plus 2 times 1 squared minus 4 times 1 plus 5. That is going to equal negative 1 plus 2 minus 4 plus 5 is 2. All right. Now we're going to plug in 2. I'm just plugging in these two numbers. I plug in 1, I plug in 2. I plug in those two numbers. See what we get. Negative 2 cubed plus 2 times 2 squared minus 4 times 2 plus 5. That's going to be negative 8 plus 8 minus 8 plus 5 equals negative 3. All right. So think about what the graph of this says. If you plug in 1, you're going to get 2. Plug in 1, get 2. If you plug in 2, you're going to get negative 3. So I don't know what this function does. I don't really care, other than I know that f of x is a continuous function. This is continuous. So whatever happens, you've got some line, some curve that goes between those 2 points. So the fact that we got a positive value 2 here and a negative value here, it simply implies that there must be something on that x-axis. There has to be some number in between 1 and 2 that makes this equal 0. There's a 0 right there. Okay, so we would say something like this. F of 1 is positive and f of 2 is negative. So there must be 0 between 1 and 2. Number 6 says use a regression calculator. So this is going to work similar to some problems that we've done in the past, but we're not doing a linear regression, and we're maybe not doing a quadratic regression. We're talking about polynomials, so it might be quadratic, but we don't exactly know yet. So the easiest thing to do, I think, is go into Goldadder Math Sites. And since we're doing a regression, Notice there are several different options. Okay, I don't want to do linear or quadratic or exponential. We're talking about polynomials because we don't really know if it's degree 2, degree 3, whatever. So polynomial regression. Now, we've never done one on Desmos, but this is kind of cool how this works. We're going to enter our x and y values in this table. So here are your x, y values. Remember, this is going to be 0. It's going to start at 1990, so this is year 0, year 2, 5, and so on. So 1990, 1992. No. 1995, 1998, 2000, 2014, 2018, 2022. Those are my X numbers. And my Y numbers, we got 127, 204, 829, 3765, 5290, 14106, 28464, 44351. Okay, so you get this table, and if you zoom out a little bit, it puts x's. It's graphing these points as x's, which is weird. You can't really tell much from this picture what it is. Is it a parabola? Is it a disco function? Is it a line? It doesn't really look like much of anything. And so what we're going to do here, we entered our data into the table. Look for the best R squared value inside the regression folders below. All right, so if this was a linear problem, okay, in order to be a line, here's your R squared value. These two numbers right here are kind of telling you how good of a fit it is. Well, going back, really in this example, we're looking at, is it quadratic, is it cubic, is it quartic? So what I want to do here, I don't really care about this one. I want to look at quadratic, second degree. See that R squared value is 0.9983, 0.9983. So here's our A, B, and C numbers. We would want to write that in as an equation. So put your A here, your B here, your C here. And let's come back to that. If it was a cubic, a third degree, it has an R squared value of 0.9986. 0.9986. So the closer the R squared value is to 1, the better a model it is. So you can see this is a little bit closer to 1, so cubic is a little bit better representation of the data. Let's look at quartic. Quartic, fourth degree. R squared, 0.9994. That's the best one of the three. Even better, 0.9994, super close to 1. So which of these models is best? We're going to say the quartic. So as for the model just means the equation. And so for the equation, we're going to need to come up with a quadratic or a cubic or a quartic equation. We know the quartic is best because of that R squared value. So I'm going to cheat a little bit here. Let's go with just so I can see these. All right, so you want to transfer those numbers over. Quadratic is going to look like this, where you've got your A number, your B number, and your C number. So my model is going to look like y equals 121.11. I'll just round off to 2 decimals. X squared. B is minus 676.41 x plus C is 700.26 or so. That's my model. For cubic, your third degree is going to look like this, where here's your A, B, C, and D numbers. So y equals, let's just call it 0.87, x cubed, 92.65, x squared, minus 448.56, plus 432.62. Quartic. It's going to have an x to the fourth in it, right? Quartic. So you put in your A, B, C, D, and F number. I think they skipped E because E is a different kind of mathematical number. Right, small, so you can fit all that in. Negative 0.31, x to the fourth, 14.66, x to the third, negative 96.05, x squared, 367.56, x minus 21.45. That's your constant. And again, which of these models is the best? Which of these equations is the best? The quartic, this one. This one's the best fit of the data because it's got the highest r squared value, the closest to 1.